Hello everyone, and welcome to our today's lecture on quantitative research methods in social sciences. My name is Dr. Haihu Guo, a lecturer at the Department of Society and Health, Faculty of Social Sciences and Humanities, Mahidol University. Today we are going to explore the essential tools used in inferential statistical analysis within the social sciences. By the end of this session, you should have a clear understanding of how and when to apply these tools in your own research. Here's what we will be covering today. First, we will define what inferential statistics is and how it differs from descriptive statistics. Then, we will look closely at three key methods: the t-test, one-way ANOVA, and correlation analysis. For each one, we will cover definitions, assumptions, step-by-step procedures, and real-life examples to help you apply them effectively. Inferential statistics allows researchers to go beyond describing the data they have and make logical conclusions about a larger population. Instead of studying every single person, we study a sample and use statistical tools to estimate population characteristics. This includes testing hypotheses, finding differences between groups, or assessing relationships between variables. Inferential statistics is essential in the social sciences because we usually work with samples, not entire populations. The t-test is one of the most commonly used methods for comparing two means. It helps us determine whether the difference between two groups is statistically significant. There are two types: the independent samples t-test, which compares two separate groups, like males versus females, and the paired samples t-test, which compares the same group of participants under two conditions, like before and after an intervention. Choosing the right type depends on your own research design. Here is a visual to help you compare the two types of t-tests. Independent samples t-test compares two different groups, like males and females. In contrast, paired samples t-test is used when we measure the same group twice, like before and after a training. This helps clarify which test should be used based on your own study design. Before we use a t-test, we need to ensure certain assumptions are met. First is normality. Your data should be approximately normally distributed. This is especially important for smaller sample sizes. Second, we assume equal variances. The variability of the two groups should be similar. Levin's test can help you check this. Last, we must consider independence. For independent samples t-test, the groups must not influence each other. For paired samples t-test, the two sets of scores should be matched logically, like pre- and post-test scores for the same people. Now, let's look at an example. Suppose we want to find out whether male and female students perform differently on exams. First, we formulate our hypothesis. The null hypothesis states there is no difference in exams. The alternative hypothesis suggests a difference exists. Then we check assumptions: normality, equal variances, and independence. After that, we run the t-test. If the p-value is less than 0.05, we reject the null hypothesis and conclude there is a statistically significant difference in exam performance between the two groups. Here is another example using the paired samples t-test. Imagine we conduct a relaxation workshop, and we want to see if participants' stress levels change after the session. We measure their stress before and after. The null hypothesis is that there is no change. We compute the difference scores for each participant, run the paired samples t-test, and check the p-value. If the result is significant, we can see that the workshop had a measurable effect on stress level. Now we move to one-way ANOVA, which stands for analysis of variance. Unlike the t-test, which compares two groups, ANOVA is used to compare 3 or more groups. One-way ANOVA focuses on one independent variable and its effect on the continuous outcome. The main question it answers is at least one group mean different from the others? It doesn't tell us which group is different, just that a difference exists somewhere. Just like the t-test, ANOVA also has key assumptions. First, normality. Each group's data should follow a normal distribution. Second, homogeneity of variances. All groups should have roughly the same spread. This can again be tested with Levin's test. Third, observations should be independent, meaning the data points in one group should not be related to those in another group. Violating these assumptions can lead to incorrect conclusions. Once you run ANOVA, you will see a F value and a P value. The F value tells you how much bigger the variation is between the groups compared to the variation within each group. The P value tells you whether the difference is statistically significant. If P is less than 0.05, you reject the null hypothesis and conclude that at least one group differs. But ANOVA does not tell you which one, just that a difference exists. To conduct a one-way ANOVA analysis, we begin by stating our hypothesis. The null hypothesis claims that all group means are equal. The alternative hypothesis suggests that at least one group differs. After checking the assumptions, we run the ANOVA test. If the F statistic is significant, that means there is a difference. We then use post hoc tests to find out which specific groups are different. Considering this example, we want to know whether academic performance varies by family income level. We divide students into low, medium, and high income groups. We run a one-way ANOVA to see if there is a significant difference in mean academic scores. If the p-value is below 0.05, we reject the null hypothesis. Then post hoc tests will show whether the low-income group performs differently from the medium or high-income groups. Next, we explore the correlation analysis. This method is used to examine the relationship between two continuous variables. The most common measure is Pearson's correlation coefficient, which ranges from -1 to 1. A positive value means the variables increase together. A negative value means as one increases, the other decreases. Values close to 0 indicate a weak relationship, while values close to -1 and 1 indicate a strong one. Correlation analysis also relies on assumptions. First, linearity. The relationship between variables should follow a straight line. Second, normality. Both variables should be normally distributed. Third, homoscedasticity. The spread of one variable should be consistent across the values of the other. And finally, independence. Each observation should be unique and not influence the others. These conditions help ensure that Pearson's correlation coefficient gives a reliable estimate. to interpret Pearson's correlation coefficients. Consider both the direction and the strength. The value from 0.2 to 0.09 is weak. 0.4 to 0.59 is moderate. 0.6 to 0.79 is strong. Also make sure to check significance. A strong correlation means little if the result isn't statistically significant. The p-value tells us that whether the relationship is likely due to chance. Here is an example. We want to see if there is a relationship between how many hours students study and their GPA. We collect data, calculate Pearson's R, and check the p-value. If R equals to 0.45 and p-value less than 0.05, we can see that there is a moderate, positive, and statistically significant relationship between study hours and GPA. This suggests that more study time is generally linked with higher academic performance. Now let's make a summary. We have covered three major inferential tools: the t-test, ANOVA, and correlation. T-tests compare two groups, either independent or paired. ANOVA compares three or more groups based on one single factor. Correlation measures the strength and direction of relationships between continuous variables. In all cases, checking assumptions and interpreting p-values are critical steps to ensure accurate results. This simplified checklist helps you apply inferential statistics properly and avoid common mistakes. First, make sure your research question is specific and measurable. Then, choose the most suitable statistical test based on your own research design and types of variables. Don't forget to check that your data meet the test assumptions, like normality and independence. Once you run the test, interpret the p-value cautiously. A small p-value suggests statistical significance, but you should also think about what it means in real-world terms. Finally, be careful not to overgeneralize your results, especially if your sample size is small or not representative of the population. Taking these steps will lead to more valid and meaningful conclusions. Thank you for your attention. I hope this session has helped you understand how to apply inferential statistics in your research work. Please take time to review these concepts and consult additional readings if needed. I look forward to seeing your progress in using these essential tools. Thank you.